I've told you we can do, an op-amp can do a lot of different functions, all right? Now we're going to look at summing amplifiers. That means where we can add up voltages, all right? You can add up voltage by using a summing amplifier. I'm also going to do it quite basically to tell you what's going to happen and how it's going to work. All right, the first one is they talk about a 2-input summing amplifier with unity gain. That means unity gain, my feedback resistor and my input resistors will have the same value. All right, that will give me a unity gain. How does it work? All right, the easiest way to explain it, how this summing amplifier is working, we also know the op-amp always tries to make the input voltage difference equal to 0, all right? Because, what is my reference here? My reference is 0. That means, if I got a resistor there and an input voltage, a positive input voltage here will give me a current that's going to flow inwards, all right? Positive voltage there will also give me a current that's going to flow inwards, all right? And we know the input impedance of this op-amp is very high, all right? Very high input impedance. That means nothing will flow into the op-amp. The amount that will flow into the op-amp is minute. You can ignore it. That means that current plus that current will give me my total current, all right? Total current times RF will give me the volt drop across there. But if I got positive here, where will the output go? It will go negative to get the current to flow in the same direction. Remember, those currents must always flow in the same direction. All right, if the current, let's say I2 was flowing in the opposite direction, I will get the difference between these two currents, all right? But if both of them flowing there, we can add them to give me my total current. Let's put some values in, just to check. Let's have a look if this thing is going to write. Let's do this. They don't want to work. All right, let's assume we make this a 10 kilo ohm resistor. I make that also a 10 kilo ohm resistor. We make the feedback resistor also 10 kilo ohm. Why 10 kilo ohm? Because we talk about unity gain. All right? I apply 5 volts here. 5 volts divided by 10K will give me what? Will give me 0.5 milliamps. Is that right? 0.5 milliamps flowing in here. Let's say here we make it 2 volts. Also positive 2 volts. That will give me a what? 0.2 milliamps. That will give me a total of 0.7 milliamps. That means 0.5 and 0.2 will give me 0.7. Hey, are you dreaming? Yes, sir. 0.7 milliamps. That means my total current will be equal to be 0.7 milliamps, all right? 0.7 milliamps multiply by a 10K, because I want the volt drop across there, will give me what? 7 volts. What will the output be? It will be minus 7, all right? That means 5 plus 2 will give me 7, all right? That is a summing amplifier. Now let's quickly have a look at the proof. We already basically did the proof, but let's quickly have a look at the proof in the book. There they state, I total is equal to I1 plus I2. We know that. And we can say V out is equal to minus I total times RF. That's also true. And then you can say V out is equal to I1 plus I2 times RF. I1 is equal to V in 1 divided by R1 plus V in 2 divided by R2 times RF. Now, if all those are equal, then we can say that V out is equal to V in divided by R plus V in 2 divided by R times R. It cancels out. Then I can say it's equal to minus V in 1 plus V in 2. All right. That is a summing amplifier with unity gain. Now here they give us a summing amplifier with n amount of inputs, all right? Again, if I make all my resistors equal, it will have unity gain. I can add up all those and it will add it up, all right? As long, what is going to be the limiting factor? What's going to be the limiting factor? What are you saying? You won't find in the book. You must think. What's going to be the limiting factor? Huh? What are you saying? Anybody, what's going to be limiting factor? No, what's the limiting factor of my output? Huh? The supply voltage. Let's say I add things up, it should give me 20 volts out. And my supply is plus 15, minus 15. Will I get 20 volts out? No. Just remember, the maximum output is limited by the supply. If I add a lot of things, I should get 100 volts out, or minus 100 volts, for example, but the supply is just plus 15, minus 15. That means the limiting factor that will limit the maximum output will be determined by the supply. You with me? All right, let's have a look at the example 13.5. They said determine the output voltage in figure 13.22. All right, I got a 10K, 10K, 10K. That means I have unity gain. All right, that's easy. I can actually say 3 plus 1 is 4 plus 8 is 12. What will the output be? Minus 12. Simple as that. But the moment I vary the resistor values, yes, you look sorry, my friend. All right, that is very simple. Again, you can also go and work out. You can work out that current, and that current. Because all of them flowing in the same direction, the total current is going to be equal to that volt drop, and that will give me my output voltage. You'll get the same. All right. Any questions? All right, now we're going to look at the amplifier. A summing amplifier with a gain greater than unity. All right. That means when I make my gain greater than unity, I will make my input resistors will be smaller than my feedback resistor. All right, if you have a look at this, my input resistors are 1K, my feedback resistor is going to be a 10K. What will the gain be? What will the gain be? It will be 10. That means my gain will be 10. If you have a look here, 0.2 and 0.5 added together will give me 0.7. Multiply by 10 will give me 7. That means the output will going to be minus 7. That means you can also go and do the following. Work out this current, work out that current, add them together because both of them are flowing inwards. Add them together and multiply by the 10K. You will get exactly the right answer. All right. Just always think about the currents. That's the easiest way. You don't know a formula, work with the currents. All right. Any questions? We can also build an averaging amplifier to determine the average. They say a summing amplifier can be made to produce a mathematical average of the input voltages. This is done by setting the ratio of RF divided by R equal to a reciprocal of the number of the inputs N. All right. That means RF divided by R is equal to 1 upon N. Let's have a look at the example of an averaging amplifier. Example 13.7 show that the amplifier in figure 13.24 produce an output whose magnitude is the mathematical average of the input voltages. All right. How many input do we have? 1, 2, 3, 4. All right. That means what should we do? We should actually divide by 4. All right. That's why now you can go and have a look at your ratio. If I take 100K divided by 25K, what will I get? What will I get? I will get 4. All right. And that will give me the average of that. 1 plus 2 will give me 3, 6, 10. If I take 10 divided by 4, what will it give me? 2.5. All right. Have a look there. What happens? It will give me minus 2.5, just 180 degrees phase shift. That means it determined the mathematical average of the inputs. All right. All right. We did previously an analog to digital converter. All right. You remember the analog to digital converter. Now we're going to do a digital to analog converter. Because why do we need things like that? Sometimes in industry you get digital signals and you got analog signals and you have to compare these things. All right. Or vice versa. Analog signals to digital or digital to analog, and that's why we normally look at analog to digital and digital to analog converters. All right. Now, first of all, we're going to look at in this case, we're going to look at the digital to analog converter. My input is going to be digital. I want the analog signal out of the circuit. And there we're going to use basically a summing amplifier to do that. But we're going to have different weights. You look at that figure there, you will notice there if I simulate a 1, it will be a high state. I will apply a positive input there to simulate a high state, and I will apply a 0 to simulate a low state. All right. We know in binary we've got basically two conditions, a high condition or a low condition. It can be 5 volts, it can be 0 volts. Just depending on the system. But now, important here, we see here, there we got 8R, 4R, 2R, and R. That one will carry the least amount of weight. More weight, more weight, weight. All right. This one will carry the highest weight. Why? 2 to the power 0 is equal to what? 1. All right. 2 to the power 1 is equal to 2, 2 to the power 2 is equal to 4, and 2 to the power 3 is equal to 8. All right. That means least amount of weight, highest weight. And then you will notice also the currents. There I will have the smallest current, here I will have the largest current. All right. Because this is the lowest resistance. And look at that, 8R, 4R. If I take 8R divided by 2, I will get 4R. If I take 4R divided by 2, I will get 2R. 2R divided by 2 will give me R. All right. We work with a system of 2 binary. All right. And here they show us basically, if I look at this example here, let's quickly look at the example. They say determine the output voltage for the digital to analog converter in figure 13.27a. The sequence of four-digit binary codes represented by the waveforms in figure 13.27b are applied to the inputs. A high level is a binary 1 and a low level is a binary 0. The least significant binary digit is D0. The least significant and the most significant. And you can also see 200K divided by 2, 100K divided by 2, 50K divided by 2 will give me 25K. All right. And here they give us the pulses for D0, for D1, for D2, and for D3. All right. As I already mentioned to you, what must we look at? The currents. Now we go and look at this. The voltage is 5 volts, all right, for a high level. I take 5 volts divided by 200k, it will give me 0.025 milliamps. 5 volts divided by 100k will give me 0.05 milliamps. 5 volts divided by 50k will give me 0.1 milliamp. And 5 volts divided by 25k will give me 0.2 milliamps. That means the least significant and the most significant, all right. And you can see each time the current increase by what? A factor of 2. If you take that, multiply by 2, I will get that. If I take that, multiply by 2, I will get that. Multiply that by 2, I will get 0.2, all right. And then they work out the output voltages. V out for D0 will give me minus 0.25 volts. V out for D1 will give me minus 0.5 volts. V out for D2 will give me minus 1 volt, and V out for D3 will give me minus 2 volts. All right. And that brings us to that. That means with 4 binary digits, I can count up to what? What's my maximum count? 16. They talk about hexadecimal, and you can have a look here. If I look at 1, it will give me minus 0.25 volts. If I look at 15, then it will give me 3.75 minus 3.75 volts. That is hexadecimal. From 0 to 15 will give me 16 count hexadecimal. Eh? That's just to show you there's 0, 1, 2, 3, 4. All right. And here they give us the different output voltage of that. Because I got a digital in, I got a analog out. Any questions? Any questions? The next one. Here they talk about R to R ladder network, digital to analog converter. The advantage of this circuit is that we're only going to have 2 types of resistors, 2R or R. That means a 1K and a 2K or what the case may be. But, very important here, if you want to simulate something, you can't leave these things open. What I mean with that, if you want to simulate a 0, it must be connected to ground reference, right? You can't leave it open. Please take note. Now, what I want you to do now here, just to know the circuit diagram, and to know that if you want to simulate a 0, it must be connected to 0 volts. It can't hang open. If you leave it open, it's not going to give you the right results. There is an explanation in the back of the book. It's a lengthy thing. You must go and draw equivalent circuits to basically do that. I'm not going to ask you to do that because we're going to waste a lot of time doing that. But you must do equivalent circuits, and I know my students, they don't like to draw equivalent circuits. But if you want to simulate a certain or determine a certain output voltage, you must go and draw the equivalent circuit to determine the output. But it's in the book. If you want to do it, you're welcome. There in the book, there they show us all the different equivalent circuits to get your different outputs. But as I already mentioned, you must connect that directly to 0 if you want to simulate a 0. If you want to simulate a 1, you must apply a positive voltage there. If you want to simulate a 0, you must connect it to 0 volts. All right. That brings us to 13.3, integrators and differentiators. I've told you, what can an op-amp do? It can add, it can subtract, it can multiply, it can compare, all right? And now we're going to look at integrators and differentiators. It can also integrate and differentiate. Right, before we're going to start with the integrator, there's a few things we should know. Things from the past. Here's an integrator. What do we have in an integrator? We got a capacitor in my feedback circuit, all right? Now I hope everybody in this class know the operation of a capacitor. I'm going to ask a few small questions and we will quickly check. And I know where I'm going to start with all my latecomer friends. They normally know everything, hey? Right. Right. When a capacitor is fully charged, will it act like an open circuit or a short circuit? I'm asking. When a capacitor is fully charged, will it act like an open circuit or a short circuit? An open circuit. Sure. All right. What are you saying? A short circuit. What are you saying? Open. What are you saying? Open. What are you saying? Short circuit. You see here? We got open circuit, short circuit. Which one's the correct one? Which one is the correct one? Open circuit or short circuit? When it's completely discharged, it'll act like what? See, now I got short and I got open. If I don't know, what can I do? Hey? All right, now listen to me. Very important. When a capacitor is completely discharged, there's no charge on it. It will act like a short circuit. When it's fully charged, there's no current flow anymore. Then it'll act like an open circuit. You with me? A fully charged capacitor will act like an open circuit. A completely discharged capacitor will act like a short circuit. It isn't a short circuit, but it will act. Why? Because it's got two plates with a dielectric material in between, all right? And when I apply a voltage across it, and it's completely discharged, it's going to charge one plate positive and negative, and there's going to be current flow, all right? It's not going to flow through the dielectric material, but it will act like a short circuit because when it's completely discharged, the charge current will be maximum. The voltage will be zero. The voltage will increase from 0 to maximum, and how many time constants? How many time constants does it need to charge a capacitor? Engineering 1. How many time constants? 5 time constants. Thank you. 5 time constants. What's a time constant? T is equal to R times C. All right, 5 time constants. The current is maximum and the current decreased to 0 also in 5 time constants. I repeat, listen to me. Capacitor completely discharged. The charging current will look like this. The voltage from 0 to maximum and 5 time constants. The current will be maximum and decrease to 0 in 5 time constants. All right, now we know something about a capacitor. All right, now we can start looking at this circuit. Now let's assume we apply a step input function. Unfortunately, these things don't want to work. I don't know why, but let's try something. Let's try this pen. I don't know. Let's try another pen. Oh, there I got something. All right. Let's say that's a step function. There's 0 volts. There's, let's say, plus 10 volt. All right. Let's assume this is a 10K resistor. 10 kilo ohm resistor. And now when I apply this step function, what will happen? I will get a current flow in that direction. You agree? That current will flow in that direction. The op-amp will always try to make the voltage difference equal to what? 0. There's 0. There should also be 0 volts. Everybody with me? But now, what will happen? What will this current be? What will that current be? It will be how many milliamps? 0.1. 10 volts divided by 10K will give me 0.1. 1 milliamp according to my calculator. Your calculators are wrong. They don't work correctly. 1 milliamp. All right. But now that capacitor was completely discharged. All right. That means, what will the feedback current be? This current that's going to flow here is also going to be 1 milliamp. How do we create that? The op-amp will take its output in a negative direction to make sure there's 1 milliamp flowing. And I will charge this capacitor here, positive on this side, negative on that side. You with me? Positive, negative. But now, we're going to look at the output. What will the output look like? If I'm going to draw the output here, let's say, there's my 0 volts. The output charge will look like this. And that will be, let's say if my supply is minus 15 volt, that will be minus 15 volts. Can't go further than minus 15 volts. You with me? But why is it a straight line? I've told you the charging curve of a capacitor look like this. There's 0. That is a charging curve. That will be around about 5 time constants. The current curve, there I got voltage. The current curve will do the following. That will be V divided by R. That will be the maximum current. All right. That is the voltage curve. That is the instantaneous voltage value, small v, and that will be small I. All right. Things from the past that you should know, but you don't know it. Now, why do we get a straight line? And there we get a curve like that. Why? I'm asking. Why? Anybody? All right, we charge it with a constant current. This current is constant 1 milliamp. Is that current constant there? No, it's not constant. We charge it with a constant current, and the constant current is 1 milliamp. You with me? That's why we get a curve like that. Please remember, we're charging it with a constant current. That's why it will give me a linear curve. At this point, it should go on forever, but what limits the output? The output is limited by the supply. I repeat that 100 times, and the students don't know that, or they don't listen to me. All right. Let's go and have a look at the proof. Do you understand what happens in the integrator? All right, here they give us a few basic formulas. That is old stuff also from Engineering 1, where we can state that the charge on a capacitor is equal to the current times the time. We can also say the charge on a capacitor is equal to the capacitor value times the voltage. we set those two equal to one another, then I can say VC, the voltage across the capacitor is equal to IC divided by my capacitance value divided by T. All right. And then they also tell us, we're going to look at that, I in is equal to V in divided by R in. And here, if you look at this equation, that's the equation for a straight line. You know that from maths, that Y is equal to mx plus B. And that is a straight line. There they also show us the currents and no currents flowing into the op-amp, and they show us IC there. And then they say IC is equal to, what's important to notice there, that IC is equal to I in. I already mentioned that to you because we're charging it with a constant current. And here they say IC is constant, and they show us it's going to give us a straight line. Here they apply input step function to the input of the integrator, same what we did on the board. And there they show us, if I apply input step function, what happens? I will have that current, and that current will be constant, and that thing will integrate till we reach minus V max. Minus V max will be determined by my supply. All right. You can't go further than the supply. I've told the maximum output of the op-amp will be determined by the supply voltage. And here's the formula for rate of output. Delta V out stands for the change in output divided by the change in time is equal to minus V in divided by R in times C. All right. Why the minus? Because if I apply a positive, my output will go negative. All right. Delta stands for the change in output voltage divided by the change in time is equal to minus V in divided by R in times C. That is the integrator. Let's have a look at the example there. Example 13.10, determine the rate of change of output voltage in response to input square wave as shown for the ideal integrator in figure 13.35a. The output voltage is initially 0, the pulse width is 100 microseconds. Have a look at this. See if you can see any mistakes, because there is a mistake. There's somewhere a mistake in the book, or in that book. I don't know the new books, if they don't also have a mistake, but there is a mistake. Is there any student that can recognize the mistake? What? Anybody? A mistake, yes or no? What? Huh? How can you say V out is more than the supply? They don't give you a supply voltage there. Where do they give you? The supply voltage will be there and there. Do they give you a supply voltage? They don't give you a supply voltage. No. How can you say V out is more than the supply? All right, if you read the question. Huh? All right, they say the pulse width is 100 microseconds. And here in the question, they use a pulse width of 200 microseconds. Now, the easiest way, changing the question, make the question, let me just show you. If you look at the question here, they say the pulse width is equal to 100 microseconds. Change that to 200 microseconds, all right? Then the question will be, then the answer will be correct. We look at this. Here they give us the circuit. The input voltage is basically a square wave because it goes from minus 2.5 to plus 2.5. That is applied to the input. Now if this thing goes positive, what will happen? I will integrate negative, all right? You can see we integrate negative. Then we go negative, then we'll integrate positive, all right? Then we go positive again, we will integrate negative. That is actually what happened. I convert that to a square wave. That means the input is a square wave. I convert that to basically a triangular wave by integrate that. First of all, they say the rate of change of output voltage during the time that the input is plus 2.5, capacitor is charging. Then you can say delta V out over delta T. V in is 2.5 volts, and it's the input resistance is 10K, and the capacitor value is equal to 0.1 microfarad value. And when we work it out, you get a value of 25 kilovolts per second. I wanted the microseconds, then I can say it's 25 millivolts per microsecond. Because I want to work out the voltage, that is for the positive input. For my negative input, it's going to be plus 25 volts per microsecond. Then I can work out delta V out. When I work out delta V out, I get 5 volts. That's why it will integrate to minus 5 and back, all right. All right, next time we will look at the practical integrator. We will look at the practical integrator, and I think that will be all for today. That means then we'll look at the practical integrator, and then we'll start looking at the differentiator. All right. Let's go on with the work. Last time we were busy with the integrator. We basically finished with the integrator. I just want to talk about the practical integrator. Now the practical integrator, we add a few additional components. First of all, we know what is RC. That's my compensating resistor to make sure my output is 0. And you will normally put a fairly high resistance value in parallel with my capacitor. If there is any drift, to make sure your output stays 0 without any input signal. Because if there is a small drift, it will start charging the capacitor and the output voltage will slowly increase, all right? And that's why we will rather put a very high resistor across there to make sure if there is no input signal that the output stay 0. That's the practical integrator. Any questions? Now we're going to look at the op-amp differentiator. Now you'll notice the difference between the integrator and the differentiator. My input is now the capacitor, and I got a feedback resistor. All right. What's going to happen in this case? What I'm going to do, I'm again going to apply an input step. Let's see what's going to happen if we apply an input step to that circuit. All right, let's say we apply input step and we make it plus 10 volt. That's my input step I'm going to apply. What will happen to the output? What do you think? What will happen to the output when I apply that? We know a completely discharged capacitor will act like what? An open circuit or a short circuit? Let's start asking. An open circuit or a short circuit? What are you saying? An open circuit. All right, I got an answer of an open circuit. What are you saying? Do you agree with him? A discharge, a completely discharged capacitor will act like an open circuit or a short circuit. Open circuit. It will act like a short circuit. I've told you in class. Please remember, a completely discharged capacitor will act like a short circuit. All right. Now, if we consider this to be a short circuit and I apply 10 volts, what will I have? Will I have small current or large current? Will the current be maximum or will it be minimum? It will be maximum because the op-amp tried to make this voltage difference 0. That means I will have maximum current. If I got maximum current here, what can I say about the current in the feedback? It should be equal to that, all right? Where will the output go? What do you think? Where will the output of the op-amp go to try to make those two currents equal? I don't think it will be able to make it equal, but where will the output go? Will it go positive or negative? Negative to what value? It will go to negative maximum. It will go maximum. All right. That means the output will shoot down to, let's say, if a supply is 15 volts to around about minus 15 volts, what will happen then? Then we'll start charging the capacitor positive there, negative there. That means now we'll start it, and it's not a constant current, we'll charge it. And when that capacitor is charged up to 10 volts, what will happen? The current will be 0. It will act like an open circuit, and the output will be basically 0 because there's no current flow here. If there's no current flow here, there won't be any current flow in my feedback resistor. All right? You with me? You understand? All right. That is, I don't think that's in the book. That's additional information I gave you just to know what's going on. All right? We're again going to look at a few formulas. In the case of the differentiator, all right, there they also tell us that IC is equal to VC divided by T times C. Same as the previous formulas we used. Now you say, so, what is going on now? Why is that current constant? Why is the current through the resistor constant? Why is IR constant? We look at this input. What is this input? It's a ramp, all right. Got a slope, it's a ramp. That's why it's constant. But if I apply a step, it's not going to be constant. All right, you with me? There's my input current. My feedback current is constant. All right, if I got a constant current flow there, what can I say about the output voltage? Sir, what is the question? Because I'm sleeping, sir. I'm dreaming. Maybe you're tired. I'm asked if that feedback current, if IR is constant, what can I say about the output voltage? It will also be a constant value. It's going to be a constant value, all right. And there they state to us, we know that IR is equal to IC, and VR is equal to IR times RF, and that's also equal to IC times RF. That means now we can say the output voltage in that case is equal to minus VC divided by T times RF times C. All right, that is for my output voltage. All right, in this case, we apply a ramp or a square wave to the differentiator. What happens? It will basically convert it to what? A square wave, all right. Because In the one case, if the input goes positive, where will my output go? The output will go negative because I use my inverting input. That means it will give me, when that current is constant, it will give me a constant output, as I already mentioned to you. When my input goes negative, what happens? The output will go positive, and because it's a constant current, it will give me a constant output voltage. All right. Any questions? Yes?
Just for general knowledge, sir. If you happen to swap the inputs, will the circuit work or will it not work?
If the?
You swap it, like you put the non-inverting side as the input.
No, because then you will have what type of feedback? Positive feedback. If you got positive feedback, it's not going to work. You can try it. It'll go to one of the limits and stay there, all right? All right, let's have a look at the example. Example 13.11, they state, determine the output voltage of the ideal op-amp differentiator in figure 13.40 for the triangular wave input shown. All right, here they show the triangular wave input. Goes from -5 to +5, and then again to -5. And they give us a time there. For basically a half cycle is 5 milliseconds. For one basically full cycle, it's equal to 10, not milliseconds, microseconds. And they ask us, we must go and do the output waveform. They say starting at t is equal to 0, the input voltage, let me just focus a little bit. That looks a little bit better. They say starting at t is equal to 0, the input voltage is positive going ramp from -5 to +5. And that is, what is the amount of change? From -5 or +5 to -5, it will give me a 10 volt change, all right? In what time? In 5 microseconds. That means we must go and have a look at the change in that time period. Then it charges to negative going ramp, ranging from +5 to -5, a -10 volt change in 5 microseconds. If I go and calculate my time constant, I've told you previously time constant is equal to R times C, and that will give me 2,2 microseconds. They say determining the slope or rate of change, Vc divided by T for the positive going ramp, and calculate the output voltage as follows. Vc divided by T is equal to 10 divided by 5 microseconds, is 2 volts per microsecond. And when I put it in the equation, I can go and work out V out. Then V out is equal to minus 4,4 volt, all right? And then for the negative going ramp, I can work it out, it's also going to be plus 4,4 volt, all right? And then we can make the drawing for the output. The output, the input and the output. There's my input voltage. VC, Vin, the triangular wave, and then I've got a square wave out that'll go from plus 4.4 to up to minus 4.4, and there's also my time period, 5 microseconds, 10, 15, and 20 microseconds. All right. That means we actually convert this to a square wave by using the differentiator. Now the practical differentiator, the practical circuit is basically the following, because we know, I've already told you, a completely discharged capacitor will act like what? A short, all right. That's why we put a fairly small resistance in series with the capacitor, all right, just to limit our current a little bit. And then there's my feedback resistor, and we also add a compensating resistor. We know about the compensating resistor from previous work. All right, there's my compensating resistor, and I put that R in series with my capacitor, just to limit the current a little bit. This will normally be a fairly small capacitance, resistor value, not a high resistance value, like in the case of the integrator. Any questions? Any questions? That brings us, to something nice, troubleshooting. Troubleshooting. Right, here we got two circuits. If I ask you to name those circuits, I'm going to ask students in the class. You must tell me what type of circuit is that, and think about it, what should the output look like? All right, playing in that direction. It shows me D1 is reverse biased, all right? D1 operates. I only have minus VZ1, all right? I don't have the 0,7. When I go to the next stage, when my input signal goes negative, the output will go positive, then it only goes to 0.7 volts, all right? That means it shows you that Zener diode is shorted, all right? It's like a piece of wire, not working like a Zener anymore. You with me? All right, when we're going to think about it, during my positive cycle, when we start with our positive cycle, where will the output go? Negative. All right, but now, this R2 is open. Do I have any reference voltage? You know about your hysteresis, your upper switching point, your lower switching point, all right? Or upper trigger point and lower trigger point. Now, because that thing is open, the output will go negative and it will stay there, all right? Because that resistor is open. We don't have that vol drop anymore. All right. All right, then I think this is the last one. All right, in this case, what happens here? Now, what is my reference now? I don't have any hysteresis anymore because R1 is open. That means I'm going to compare the input signal with what? 0. All right. That's why it will go to the Zener voltages. I'm going to compare it with 0. All right. Because R1 is open. Now it works as a zero level detector. I won't have any hysteresis. All right. That is the end of the story for this chapter. You must go and do all the problems, the back of the chapter, and I will check in the first test if you know your work. When is that? I will let you know. Start studying and start doing your work. No, it's not going to be next week. We must still do some other work. I'm going to give you a few circuits. You must write them down, and you must go and do them at home, and then we're going to discuss it in class. And I'm going to ask you questions, all right? Yes. That is special circuits. There will be 10 marks on that in the first test. When you're not finished, you don't have to put your books away. You last in class, and then you want to put your books away. All right. I repeat, you must make drawings of all these sketches, do them at home, and then we'll discuss it in class. All right.
10 marks.
10 marks.
How much is the test out of?
35. All my tests are 35, and that'll be 10 marks out of 35. Now you can do your calculations. And please take note, you won't be able to solve those things by using a formula. You should know the operation of the circuit. All right. Huh? Any?
Some theory questions.
Theory, I can ask theory, I can ask proofs, anything. That's your choice to work out what I'm going to ask, but don't make a mistake, eh? Sketches also. All right, you can start writing down. There's the first one. Oh, sorry. You won't see it. Now there it's on